Have you ever really stopped to think about what's going on inside your phone or your computer? I mean, really going on? Today, we're going to do something kind of wild. We're going to build a computer right from the ground up. We'll start with the absolute simplest idea you can imagine and build layer by layer by layer until we have a machine that can actually run a program.
So let's start with a question that sounds a little strange. You've got this incredibly complex smartphone in your pocket, right? A universe of technology. And then you've got a plain old light switch on the wall. What on earth could those two things possibly have in common?
And that's it. That is the secret, right there. At its absolute core, every single digital computer on this planet, no matter how powerful, operates on this one simple principle. It's either on or it's off. It's yes or it's no. It's a 1 or a 0.
So how do we get from a simple on-off switch all the way to a running program? Well, here's the game plan. We're going to start with that magic switch, then use it to forge tools that can actually think. From there, we'll build smarter components, give our machine a memory, then a brain, and finally, we'll learn how to actually talk to it. It's a journey, an ascent, from a single bit to a full computer.
Okay, first things first, we have to define the fundamental particle of our new digital universe. And to do that, we need to bring some serious order to the chaos of the real physical world. You see, the world around us is analog. It's a messy, continuous flow of information. Think of a dimmer switch for a light. It can be 25% bright, 73% bright, any value in between. That's just too complicated to build a reliable machine. So engineers came up with a brilliant idea: a digital abstraction. We just make a rule. We're only going to pay attention to two states: a high voltage, which we'll call 1, and a low voltage, which we'll call 0. And just like that, we've turned the messy, analog world into a clean, predictable, digital one. And that simple two-state concept has a name you've definitely heard before: the bit, a binary digit. This is the hero of our story. It's the single Lego block from which we are going to build absolutely everything else. Every photo you take, every song you stream, every line of code in an app is, at the end of the day, just a gigantic collection of these simple ones and zeros. So now we have our raw material, the bit. But, a pile of Legos is just a pile of Legos. It's not a spaceship. We need some tools to start shaping these bits into something that can perform logic, something that can, for lack of a better word, think. And this is a really important idea to get your head around. What we're talking about from here on out isn't just theory. These are blueprints for real physical circuits that follow predictable rules. Once you accept that we can physically build something that works in this simple on-off way, you realize, oh my gosh, we can build anything. Let's start with one of our most fundamental tools. This is the NAND gate. Just look at its truth table here. It takes two inputs, let's call them A and B, and it gives you one output. And the rule is so simple. The output is always a 1 unless both A and B are 1. That's it. It's a tiny little decision maker. And here's the truly amazing part. You can build every other logic function you can possibly imagine using only this one type of gate. It's what we call functionally complete.
So what's actually going on inside this little decision maker? Well, we can peek under the hood for a second. A NAND gate is made of just 4 transistors. And a transistor, for our purposes, is just a microscopic switch that you can turn on or off with electricity. By arranging these 4 switches in this very specific pattern, we create a real physical circuit that perfectly follows that NAND rule we just saw. We've just connected an abstract idea to physical reality. Pretty cool, right? Okay, so we have bits. We have our first tool, the logic gate. Now it's time to level up. We're going to start combining these simple tools into more powerful, more complex components. This is where the whole building in layers thing really starts to pay off. Meet the multiplexer, or MUX for short. The easiest way to think about this is like a digital train switch. You've got 2 data tracks coming in, D0 and D1, and 1 track going out, Y. And then you have a select signal, S, which is like the switch operator. If S is 0, it connects the D0 track to the output. If S is 1, it connects the D1 track. It's a fundamental circuit for choosing between different streams of information. And here is where the magic of abstraction really kicks in. Once we've built our multiplexer out of a handful of NAND gates, we can basically draw a box around it and forget how it works on the inside. We just created a new, more powerful component, All we care about now is what it does, what goes in and what comes out. This is the only way to manage the mind-boggling complexity of a modern chip.
And the really powerful takeaway here is that we can now use our new bigger blocks to build even bigger blocks. For instance, we can take 3 of those simple 2-to-1 multiplexers we just made, wire them together in a clever way, and boom, we have a more powerful 4-to-1 multiplexer. We're building with bigger and bigger Legos. This concept, modular design, is how engineers can design systems with literally billions of transistors without losing their minds. All right, everything we've built so far is what's called combinational logic. The output depends only on the inputs at that exact moment. They have no memory, no sense of the past. To build a row computer, we have to introduce the element of time. Our machine needs a way to store information. It needs memory. And this little guy is the key. It's called a D flip-flop, and it is the fundamental building block of computer memory. Unlike a simple logic gate, it doesn't just react instantly. It waits. It has a data input, D, and a special clock input. Think of that clock as the steady heartbeat of the computer. It's only on the tick of that clock, the precise moment the signal goes from low to high, that the flip-flop even looks at its input and copies that value to its output. Until the next tick, it just holds on to the last value. It remembers. This is a 1-bit memory cell. Let's take stock. We've got logic gates to think. We've got flip-flops to remember. We now have all the fundamental pieces we need. It's time. Let's assemble them into the brain of our machine, the central processing unit, the CPU. So what does a processor actually do all day? Well, at its core, it just does a very simple, very repetitive dance. We call it the instruction cycle. First, it fetches an instruction from memory. Next, it decodes that instruction to figure out what it's being told to do. Am I adding, subtracting, moving data? Then it executes that command using the very logic circuits we've been talking about. Finally, it might write a result back somewhere. And then it does it all again, and again, and again, billions of times every single second. Now, the crucial thing to realize is that this hardware engine we've built, it doesn't understand words like add or subtract. It only understands patterns of bits. The complete list of commands it recognizes and the specific binary pattern for each one is called its Instruction Set Architecture, or ISA. You can think of the ISA as the ultimate contract, the interface between the physical hardware we've built and the software that's going to run on top of it. And with that, we've reached our final level of abstraction. We have a real physical machine that understands a very specific binary language. The last piece of the puzzle is, how do we, as humans with our complex ideas, communicate with it? Well, we start at the very top with something called a high-level programming language, like C. This line of code is super easy for a human to read and understand. Add F and G, add H and I, then subtract the 2 results. Simple enough for us, right? But to our brand new processor, this is complete gibberish. So a special program called a compiler comes in and translates that one line of C into several much simpler steps in a language called assembly. This is getting closer to the machine. Think of it as a symbolic but still human-readable version of the processor's instructions. Each line here corresponds to one basic operation the CPU can perform, like adding the values in 2 of its little memory scratch pads, which we call registers. We're almost there. And here it is, the final step. Another program, this one called an assembler, takes each of those assembly commands and translates it into the raw binary that the machine actually understands. That add command becomes this specific 32-bit pattern of 1s and 0s. This is what our processor fetches from memory. This is what flows through the logic gates we designed. This is the true language of the machine. So there you have it. From a simple on-off switch all the way up the ladder of abstraction, we've built a complete computing system. From physics to transistors to gates to a CPU that can execute a program. We have a machine that follows a list of binary instructions with perfect, blindingly fast obedience. The final lingering question is, how do we arrange those simple 1s and 0s into instructions that can create art, connect billions of people, or discover new medicines? Well, that is the magic of software.